Tonight on Dark Matter Nap, we are going to travel to the absolute edge of illumination. When we think about light, we think of it as an unstoppable eternal force. It is the fastest entity in the physical universe, screaming across the vacuum of space at 186,000 miles per second. We see starlight that has traveled for billions of years, crossing unimaginable voids just to strike the lenses of our telescopes and the retinas of our eyes. We naturally assume that if you give a photon enough time, it can cross any distance, pierce any darkness, and eventually reach any destination in the cosmos. We believe that light is the ruler of reality, the ultimate conqueror of the void. But astrophysics reveals a far more claustrophobic and terrifying truth. Light is not unstoppable. It is highly fragile, bound and restricted by the brutal, unyielding geometry of space and time. There are absolute physical boundaries where the journey of a photon simply fails. There are regions of the universe where light is violently stretched into nothingness, trapped in infinite circles, physically blocked by cosmic walls, or entirely forbidden from entering by the expanding architecture of the vacuum. Tonight, we will break down the exact coordinates of these cosmic dead ends. We will explore the invisible wall of the expanding universe, analyze the strange, mind-bending physics of the black hole photon sphere, travel backward to the impenetrable fog of the Big Bang, and witness the chronological final spark of light at the very end of time. Before we step out of the light and into the deep dark, take a second to like this video and subscribe to the channel. It helps us reach more curious minds like yours. Now, settle in, turn off the lights, and let's travel to the last place light can reach. To begin our journey, we do not need to look at the edge of the universe. We can see the fragility of light right here in our own solar system, dictated by a fundamental rule of physics known as the inverse square law. Light is emitted radially in all directions from a star, spreading out across the volume of a sphere. As that sphere gets larger, the original amount of light must cover a vastly larger area. This means the intensity of light drops exponentially the further you travel from the source. On Earth, we are bathed in the brilliant, blinding warmth of our sun. But as you move outward through the solar system, that light rapidly decays. By the time you reach Jupiter, the sun is just a painfully bright star in a pitch-black sky. By the time you reach Pluto, roughly 3.6 billion miles away, the sunlight is intensely weak. High noon on Pluto looks exactly like a dim, twilight evening on Earth after the sun has already set. If you keep traveling outward to the Oort cloud, the icy shell of debris marking the gravitational edge of our solar system, the sun becomes completely indistinguishable from the other stars in the sky. The light has not stopped, but it has become so scattered, so infinitesimally thin, that it can no longer illuminate anything. The first boundary of light is simply distance. The universe is so unfathomably large that light naturally dilutes itself into the dark. But there are much harder boundaries than mere distance. There are physical walls in space. When we look up at the Milky Way stretching across the night sky, we see glowing clouds of stars, but we also see massive pitch-black rifts cutting through the light. For centuries, ancient astronomers believed these dark patches were literal holes in the heavens, places where there were no stars at all. Modern astrophysics proved that these are not holes, they are molecular clouds. They are vast, dense nebulae made of cold, cosmic dust and complex molecules that are completely opaque to visible light. These dust clouds create a phenomenon known as the zone of avoidance. Our own solar system sits inside the disk of the Milky Way, roughly 26,000 light-years from the galactic center. When we try to look toward the supermassive black hole at the heart of our galaxy, our optical telescopes see absolutely nothing but a dark, impenetrable wall. The interstellar dust absorbs the visible photons, completely blocking our view of the most densely populated region of our own cosmic neighborhood. The light from millions of massive, brilliant stars simply strikes this dust and dies, its energy converted into minor, invisible heat. The universe is filled with these dark vaults, massive regions of space completely shielded from the illumination of the surrounding cosmos, proving that light can be stopped by something as simple and unassuming as cold dust. If we look past the dust and try to look further out into the vast, expanding architecture of the cosmos, we encounter a boundary that is not made of matter but made of space-time itself. For a long time, humanity believed that if we just waited long enough, the light from every single galaxy in the universe would eventually reach our sky. It was just a matter of waiting for the photons to cross the distance. But in the late 1990s, the discovery of dark energy shattered that assumption completely. Dark energy is a mysterious, repulsive force that is actively stretching the fabric of space-time. And because space is expanding everywhere at once, the cumulative speed of this expansion increases the further out you look. Imagine a photon of light leaving a distant galaxy tonight, perfectly aimed at Earth. As that photon begins its journey, traveling at the absolute cosmic speed limit of 186,000 miles per second, the space beneath it is actively stretching. If that galaxy is sitting beyond a specific mathematical boundary, roughly 16 billion light-years away from us, the space between us is expanding faster than the speed of light itself. This creates an unyielding physical wall known as the cosmic event horizon. The photon is moving toward us as fast as the laws of physics allow, but the ground it is traveling across is acting like a cosmic treadmill running in reverse. The photon will never make progress. It will fly through the cold intergalactic void for 1 billion years, 1 trillion years, 1 quadrillion years, and it will only ever get further away from us. That photon is permanently marooned in the intergalactic desert. This means there is a hard, spherical boundary around our planet marking the absolute last place our light can ever reach, and the last place from which light can ever reach us. Every single star, nebula, and galaxy sitting beyond that line is completely severed from our reality. We can never see them as they are today, and they can never see us. The universe has built an invisible, inescapable quarantine wall out of expanding space. And because the expansion of the universe is accelerating, this horizon is shrinking. Every day, thousands of galaxies cross over this invisible line, their light permanently cut off from our future. But what happens to the light that is already trapped inside this expansion? If a photon is flying through the intergalactic void, trying to cross the growing chasm between galaxy clusters before the horizon overtakes it, it does not remain untouched. It faces a slow, agonizing death through a process known as cosmic redshift. Light travels as a wave. The distance between the peaks of that wave dictates its color and its energy. Blue light has short, tightly packed waves indicating high energy. Red light has longer, stretched-out waves indicating lower energy. But as a photon travels across the deep universe, the very fabric of space-time it is riding on is actively stretching. As space stretches, the photon's wavelength is physically pulled apart along with it. If you stand outside on a clear night, you are bathed in the oldest light in existence, the cosmic microwave background. This is the literal flash of the Big Bang, the brilliant, blinding white light of creation that filled the early universe, but you cannot see it with your naked eye. Over the last 13.8 billion years, as that ancient light traveled across the expanding void, its wavelength was systematically stretched. It was pulled past the visible spectrum, past infrared, and flattened out into long, weak microwaves. The light didn't hit a physical wall, it was simply exhausted by the stretching of space. In the deep future, as dark energy continues to accelerate, this stretching will become terminal. Trillions of years from now, the light leaving the remaining distant galaxies will be stretched so severely that its wavelength will become larger than the observable universe itself. The waves will completely flatline. The energy of the photon will drop to absolute zero. The light will not be blocked by a planet or a dust cloud. It will simply fade away into the cold, silent background of the void, completely erased by the expanding geometry of the cosmos. The universe will quietly stretch the light out of existence. If the expansion of space is the slow, agonizing death of light, there is another boundary in the universe that represents a sudden, violent, and inescapable trap. To find it, we must travel toward the most extreme gravitational engines in reality, black holes. We all know that the core of a black hole, the singularity, is a place of infinite density where gravity is so overwhelming that not even light can escape. The boundary marking the absolute point of no return is called the event horizon. Once light crosses the event horizon, it is gone forever, pulled inward toward the crush of the singularity, permanently removed from the observable universe. But there is a specific, razor-thin boundary existing just outside the event horizon. It is a place where the gravity is incredibly intense, but just barely weak enough to allow light to survive. This mathematical boundary is located exactly 1.5 times the radius of the event horizon. It is called the photon sphere. When light from a distant star travels close to a black hole, the massive gravity warps the spacetime fabric, bending the path of the light. If a photon passes too far away, its path is simply bent, and it flies off in a new direction, a process known as gravitational lensing. If it passes too close, it crosses the event horizon and spirals down into the darkness. But if a photon hits the exact, precise trajectory of the photon sphere, the bending of space perfectly matches the speed of the light. The photon is captured, but it doesn't fall in. Instead, it is forced into a permanent circular orbit around the black hole. The photon sphere is a shell of pure, trapped light. Billions of years of starlight, radiation, and the glowing emissions of cosmic dust are caught in this violent, invisible waiting room, circling the black hole at 186,000 miles per second. If you were wearing an indestructible spacesuit and you somehow managed to hover exactly inside the photon sphere, looking straight ahead, the visual geometry of the universe would shatter your human intuition. Because light is actively orbiting the black hole in a perfect circle, the light bouncing off the back of your own spacesuit would travel all the way around the black hole and hit you right in the eyes. If you looked straight ahead, you would see the back of your own head. The photon sphere is the absolute last place light can exist as a structured, traveling entity before it is swallowed by oblivion. It is the cosmic edge of the abyss, a glowing halo of trapped time and trapped history, spinning in the dark until the end of the universe. But what happens to the light that fails to hit the perfect angle of the photon sphere? What happens to the light that is just a fraction of a millimeter too close and crosses the event horizon? According to the established laws of general relativity, once a photon passes the event horizon, the fundamental geometry of space and time is violently swapped. Inside a black hole, space no longer points outward, all possible directions point inward toward the singularity. For the photon, there is no physical concept of turning back or flying away, because the past is literally located outside the horizon and the future is physically located at the singularity. As the photon falls deeper into the gravity well, it experiences a terrifying phenomenon known as extreme blue shift. As it accelerates down the gravitational cliff, the light wave is compressed violently, gaining massive amounts of energy, but it will never illuminate the interior of the black hole. There is no solid surface to strike, no walls to bounce off, and no observer to see it. The photon plunges directly into the central singularity, a point of infinite density where the known laws of physics completely break down and cease to function. The light is crushed out of existence, its pure energetic value added to the total mass of the black hole. The singularity is the ultimate final graveyard of light, a place where illumination is physically dismantled and converted into raw gravitational weight. These are the boundaries of space and gravity, but light is also limited by a chronological boundary in the past. When we look up at the stars, we are looking back in time. Because light takes time to travel, seeing a star a million light years away means seeing it as it was a million years ago. Telescopes are literal time machines. So it stands to reason that if we build a telescope powerful enough, we should be able to look all the way back to the exact second the Big Bang occurred and see the birth of the universe. But physics forbids this. There is a temporal wall that light cannot penetrate, a boundary known as the surface of last scattering. For the first 380,000 years after the Big Bang, the universe was incredibly hot and dense. It was a boiling, opaque soup of free-floating protons, electrons, and intense radiation. In this extreme environment, light could not travel. The moment a photon was emitted, it immediately slammed into a free electron, bouncing wildly inside the plasma. The universe was completely glowing, but it was essentially a solid wall of illuminated fog. It was utterly opaque. It wasn't until the universe expanded and cooled down to roughly 5,000 degrees that the protons and electrons finally slowed down enough to combine and form the first neutral hydrogen atoms. This event is called recombination. The exact moment the electrons were locked into atomic orbits, the fog lifted. Space instantly became transparent, and light was finally free to travel in straight lines across the void. That flash of released light is the cosmic microwave background we observe today, but it also represents an absolute physical barrier. No optical telescope, no matter how large or technologically advanced, can ever see anything older than 380,000 years after the Big Bang. If you try to look further back, you just hit the glowing wall of the primordial plasma. It is the absolute first place light could ever exist as a free entity, and it serves as a sealed door, locking away the visual history of the universe's creation. We have explored the spatial boundaries of light, the gravitational traps, and the chronological wall of the past. But there is one final boundary we must face. It is not a place in space, but a coordinate in the deep, unfathomable future. What is the chronological last place light will ever exist? To find it, we must travel to the absolute end of the cosmic timeline, far past the lifespan of humanity, past the death of our sun, and into an epoch known as the Black Hole Era. By 100 trillion years from now, the era of starlight will be completely over. The universe's supply of raw hydrogen gas will have been entirely exhausted. The brilliant blue giants, the stable yellow suns, and the long-lived red dwarfs will have all burned through their fuel and faded into cold, dark husks. The universe will be a freezing, expanding desert populated only by dead planets, frozen stellar corpses called black dwarfs, neutron stars, and supermassive black holes. The cosmos will be entirely pitch black. There will be no fusion, no starlight, and no illuminated nebulas. But even in this absolute, staggering dark, physics dictates that black holes are not eternal. Due to the bizarre and unyielding laws of quantum mechanics, black holes slowly, silently leak mass into space through a process called Hawking radiation. At the very edge of the event horizon, pairs of virtual particles are constantly blinking into existence. Occasionally, one particle falls into the black hole while the other escapes, slowly draining the black hole's mass. Over unfathomable time scales, stretching to a googol of years, a one followed by 100 zeros, these absolute titans of gravity will slowly evaporate into nothingness. As a black hole loses mass, the rate of its evaporation accelerates and its temperature spikes exponentially. In the final fraction of a second of its existence, a black hole does not just quietly fade away, it detonates. The death of a supermassive black hole releases a sudden, violent explosion of pure, high-energy gamma-ray light. In a universe that has been completely dead, cold, and entirely black for trillions upon trillions of years, this explosion will be a solitary, blinding flash of pure illumination. This flash is the final act of light in our universe. The gamma rays will shoot out into the expanding empty void, but because dark energy has spent the last googol of years stretching the universe to an unimaginable size, these final photons will have absolutely nothing to strike. There will be no planets to illuminate, no eyes to see them, and no dust to warm. They will fly through a completely empty, hyper-expanded vacuum. Within a fraction of a cosmic second, the accelerating expansion of space will catch hold of them. Their wavelengths will be violently stretched, pulling them apart, flattening them into weak radio waves, and finally dissolving them completely into the absolute zero of the heat death. When that final photon flatlines, the history of light in our universe will officially end. The cosmos will enter the dark era, a state of perfect, undisturbed thermodynamic stasis. There will be no energy, no motion, and no illumination ever again. The universe will return to the absolute dark from which it was born. This terrifying chronological timeline leads us to a profound and deeply beautiful realization about our everyday existence. We look at the stars, the sun, and the bright blue sky of our planet, and we naturally assume that light is the default state of the universe. We think of the dark as merely the absence of light, a temporary shadow waiting to be filled. But astrophysics proves the exact opposite. The absolute dark, the frozen void, the unyielding emptiness, that is the true, permanent baseline of reality. Light is a highly unstable, temporary rebellion against the emptiness. It is a brief, fragile spark allowed to exist only during this tiny, volatile window of cosmic history. The universe is not a place of eternal light. It is a dark room where a match has been briefly struck. We are alive in the era of stars. We exist exactly at the right moment to witness the universe while it is still illuminated, while the cosmic web is still glowing, and while photons can still cross the interstellar gulfs to bring us the history of the galaxy. Thank you for joining me tonight on this massive 30-minute journey to the edge of illumination here on Dark Matter Nap. If this deep exploration of the limits of light, the invisible expanding treadmills of space, and the terrifying traps of black holes challenged the way you view the night sky or made you appreciate the fragile photons that warm our world, please take a moment to like this video and subscribe to the channel. Your continued support is the exact engine that helps us create these late-night, immersive deep dives into the absolute mysteries of our existence. The next time you flip a light switch in a dark room or watch the sunrise slowly paint the morning horizon, do not take it for granted. Appreciate that light not just as a simple physical utility, but as a beautiful, fleeting masterpiece. It is a fragile wave of energy pushing back against a universe that is mathematically destined for the dark. Sleep well tonight, knowing that our local star is still burning bright, that the photons are still reaching our eyes, and that the shadows have not yet won. Good night, and may your dreams reach far beyond the absolute horizon.